Devhare. Today we are going to discuss topic differential equations. So before going to our main topic, we'll discuss some application part of differential equations. So study of differential equation is of prime importance because of its application in almost all the engineering fields. Some examples are analysis of electrical network, motion of fluid through porous media, heat transfer through spherical or cylindrical shells, decay of radioactive elements, projectile motions. Okay. Even medical sciences have not escaped the involvement of differential equations. Concentration of sugar in blood is analyzed by a mathematical model involving differential equation. Studies of blood flow through the arteries, kidneys, and the various organs of the body have attracted the attention of scientists working in the field of biomedical engineering. So, ordinary or partial differential equations play an important role in different kinds of models representing various phenomena. So, differential equations are also used in modeling of day-to-day life situations like concentration of traffic on roads in urban areas, arrival of customers in shopping malls, landing of planes at the crowded airports, and so on. So, let's come to our main part, that is differential equation. First, we'll see the definition of differential equations. Okay. So, what is meant by differential equations? So, an equation which involves derivatives or differential coefficients like dy by dx, okay, is called a differential equation. And here it is one example of a differential equation, that is dy by dx equal to cos x. Okay, this is a simple example of differential equation. Now, what are the outcomes of or objectives of these differential equations? So first is understand the types of differential equations and solution of the first order first degree differential equation. Next is compare differential methods of solving differential equations and apply suitable one to solve examples. And so last one is construct their own examples of differential equation and interpret its solution. Now let's take some more examples of differential equations. Okay, so this look at this second example. It is a second order differential equation. Okay, so here d2y by dx square, therefore here higher order derivative is there. Next is, there are some more examples of differential equation. Okay, now again there are two types of differential equations. Okay, ordinary differential equation and partial differential equation. So depending upon the number of independent variables, okay, depending upon the number of independent variables, there are two types. So first one is ordinary differential equation. So its definition says that a differential equation is said to be an ordinary differential equation if all differential coefficients involve only one independent variable. So these are the examples of ordinary differential equation. Okay, the next type is partial differential equation. A differential equation is said to be partial differential equation if all differential coefficients involve two or more independent variables. Okay, so here is an example of partial differential equation. So here two independent variables are there, x and y, and u is a dependent variable. Okay, so basic difference between partial differential equation and ordinary differential equation is that ordinary differential equation means only one independent variable. Partial differential equations involves two or more independent variables. Okay, this is the basic difference. Okay, now next definition is order of a differential equation. So what is meant by order? The order of differential equation is the order of the highest derivative appearing in that equation. Okay. Now let's take example. Okay. So dy by dx equal to cos x. Look at this example. The highest order derivative in this example is dy by dx. Therefore, equation in this example is of the first order. Now let's come to this second example. Okay. If we look at this example, the highest order derivative in this example is 2. Okay. And therefore, order of this differential equation is 2. That is second order differential equation. Now the next part is degree of a differential equation. So the degree of differential equation is nothing but the highest order derivative. It's nothing but the power or index of the highest order derivative in the differential equation when it is free from radicals and fractions. Okay. Now let's come to again same example. Okay. Dy by dx equal to cos x. If we look at this example, it is already first order derivative of first order differential equation. Now look at its power. Its power is 1 and therefore degree of this differential equation is 1. Similarly for the second, highest order derivative is d2y by dx square and therefore its power is 1, hence degree of given differential equation is 1. Now the highest derivative in this third example. Okay, highest derivative in this third example is d2y by dx square and look at its power. Okay, so its power is 3 and therefore degree of this differential equation is 3. Okay, so this is a basic difference in order and degree. Okay, degree means take power of highest order derivative. Okay, now let's come towards the examples. So first example is this: find the order and degree of this differential equation. If we look at this differential equation, so its power contains 3 by 2, that is a fraction. Okay, so first we have to make this equation fraction free. Okay, so for that what we have to do? So we have to do the square of both sides. Okay, that means we have to take square of both sides. Okay, so therefore to make the power fraction free, squaring on both sides, okay, we'll get the new equation. This is our new equation, and if we look at this equation, it is now its power is fraction free. So now highest order derivative in this differential equation is d3y by dx cube, that is third order. And if we see the power of this third order derivative is 2, and therefore the order of this differential equation is 3 and degree of this differential equation is 2. Okay, so now let's take one more example. Okay, now look at this differential equation. Here dy by dx plus 54 upon, at this denominator dy by dx term is there. Okay, so how to find its order and degree? So this is our differential equation. Now take cross multiplication. Okay, now take the cross multiplication. Therefore our differential equation becomes like this. Okay, d2 y by dx with square plus 54 equal to 10 into dy by dx, and if we look at this equation, its highest order derivative is dy by dx. Okay, and if we look at its power, okay, if we look at its power, it is 2, and therefore order is 1 and degree is 2 here. Okay, so next is what is the solution of differential equation. Okay, so how we can find solution of differential equation? So basically we'll see the definition of solution of a differential equation. A solution of a differential equation means is any relation between dependent and independent variable and which satisfies the given differential equation. Okay, now again there are two subtypes, that general solution and particular solution. So we'll see this concept by using an example, okay, so that it will be more clear to you. So consider this example, d2y by dx square equal to 0. Okay, so in this differential equation, x is independent variable and y is dependent variable. So integrating this equation, will get dy by dx equal to some constant c1. Okay, so constant of integration. So again integrate this differential equation. Okay, so again integrate this differential equation, then we get y equal to c1x plus c2. So therefore this y equal to c1x plus c2 is the solution of the given differential equation. Okay, so moreover, if y equal to, if we take y equal to c1x or y equal to c2 or y equal to 2x plus 1 or y equal to minus 3x or y equal to 8, these all are the solutions of this given differential equation. Okay, so all the solutions either involves constant or not involve any constant. So thus, depending upon the presence of an arbitrary constants in the solution of differential equation, there are two subtypes. Okay, so general solution and particular solution. First we'll see the general solution. Okay, a solution of a differential equation in which the number of arbitrary constant is equal to the order of differential equation, then it is called as general solution of that differential equation. Means what? If order of given differential equation is 2, then solution of that differential equation contains 2 arbitrary constants. Okay, so if order of differential equation is 3, then its general solution contains 3 arbitrary constants. So general solution contains number of arbitrary constant equal to order of differential equation. Now if we assign particular value, so if we look at this equation d2y by dx square equal to 0, then this y equal to c1x plus c2, this is a general solution of this given differential equation. Okay, and it is only one solution, or we can say that this general solution is unique. But if we assign particular values, this c1 and c2, okay, so if we assign particular values to this c1 and c2, then we get many particular solutions. Okay, so let's see the definition of particular solution. A solution of differential equation which is obtained from this general solution. Okay, so by assigning particular values to the arbitrary constants. Okay, so it is called the particular solution of the differential equation. So again take same example. Okay, d2y by dx square equal to 0 and its general solution is c1x plus c2. Okay, so if we assign particular values for the c1 and c2, then we get, okay, if we take c1 equal to 2 and c2 equal to 4, then we get y equal to 2x plus 4, y equal to minus x, y equal to, and so on. So these all are the particular solution of this differential equation. So here are some observations regarding this solutions. Okay, so if any differential equation is given, we can find its unique general solution and infinitely many particular solution. Okay, so therefore its general solution is always unique. If we have a particular solution, then we can find the corresponding differential equations. Okay? If we have a particular solution, then we can find its corresponding differential equations, and these differential equations are not unique. Okay, again, if we find differential equation from its particular solution, then these differential equations are not unique. So consider this example: y equal to 2. Okay, is a particular solution of these differential equations. Okay, dy by dx equal to 0, d2y by dx equal to 0, and again also this differential equation and many more. The last observation is, if we have a general solution, then we can find the corresponding unique differential equation and vice versa. That means if we have a differential equation, then its general solution is unique, and if we have a general solution and if we find the corresponding differential equation, so it will be again unique. Okay, so the next is formation of ordinary differential equation. Okay, so in this we particularly study the ordinary differential equation. Okay, so an ordinary differential equation can be formed by eliminating certain arbitrary constants from its general solution. Okay, so if there are n arbitrary constant in the general solution, then it is to be differentiated n times, and eliminating those n arbitrary constants from this n plus 1 equations will get the required nth order differential equations. That means we have to eliminate the arbitrary constant from the given solution. Okay, so let's come to the example. Question is, find the differential equation whose general solution is this. Okay, now there are two arbitrary constants c1 and c2. That means we have to differentiate this twice. Okay, so we have to differentiate this equation twice, and we have to eliminate this constant c1 and c2. So to find its solution, yes, so consider here y equal to c1x plus c2 e raised to x. So now first differentiate this with respect to x. If we differentiate, then we get derivative dy by dx equal to derivative of this first term is c1 plus derivative of this second term is c2 e raised to x. Okay, now again differentiate this with respect to x. So therefore d2y by dx square equal to, this c1 is constant, therefore its derivative becomes 0, and it is equal to c2 e raised to x. Now, so from this equation 2 and 3, we can find the value of c2 e raised to x and c1. Okay, so value of c2 e raised to x is d2y by dx square in terms of differential. So substitute this value in this equation number 2. Therefore our equation 2 becomes dy by dx equal to c1 plus d2y by dx square. Now from this equation we can find value of c1. So value of c1 is dy by dx minus d2y by dx square. So now what we have, value of c2 e raised to x and value of c1. So substitute these two values of constant in this first equation. Okay, therefore y equal to this value of this differential equation, and if we simplify this differential equation, then we get final form of differential equation. Okay, and it is the required solution of the given equation. Okay, and it is a second order differential equation. So this is about the formation of differential equation. So let's take one more example on this topic, that is, find a differential equation whose general solution is given by this equation, okay, where this a and b are arbitrary constants. So again here two arbitrary constants, okay, so that means we have to differentiate this equation two times, okay, to eliminate this arbitrary constant. So first differentiate with respect to x. So first equation is dy by dx 4a raised to 4x plus derivative of the second term is 3b raised to 3x. Now again differentiate this with respect to x, okay. Therefore d2y by dx square equal to 4 into 4 16 and here 9. Now multiply this equation 2 by 4 and subtract it from equation 3. Then we get, okay, why we are doing all these things? Because we have to eliminate these constants from this equation, okay, and convert it in differential equation. So to remove these constants, first we multiply this equation 2 by 4 and equation, and we'll subtract this equation from this third equation, okay. Then we get 4 dy by dx minus d2y by dx square, and therefore our right hand side becomes, this 2 will get cancelled, and here 12 minus 9, that will be 3b raised to 3x. So from which we can find value of b e 3 raised to 3x, okay. Now the next step is multiply again equation 2 by 3 and subtract it from equation 3. Then we get, yes, we will get value of a e raised to 4x. So now we got two values, a e raised to 4x and a e raised to 3x, okay. So substitute all these values in first equation, that is y equal to y equal to a e raised to 4x plus b e raised to 3x. So if after substitution, then and if we simplify this, then we get y equal to this equation, and if we simplify further, then we get differential equation, that is d2y by dx square minus 7 dy by dx plus 12y equal to 0, and is the required second order differential equation. Why it is second order? Because this equation y equal to a e raised to 4x plus b raised to 3x, it contains two arbitrary constants, okay. Now these are the examples of formation of differential equation. So for this time we'll stop here, and in the next video we'll go for further discussion or further types of ordinary differential equation, okay. So thank you.